In this presentation, I'm going to describe how to do the exercise, how to do the exercises 1.5 and 1.6. Let's see the outline of the exercises. Well, the exercise 1.5 is about the watershed delineation using QGIS. First of all, we are going to delineate the drainage network using the string order proposed by Strahler. Then we will define the coordinates of the site of interest in the basin under study and delineate the tributary basin up to that site. The tributary basin would be what we call the domain outline that we will use in the application of the hydrobit flood model. Okay, that's the first exercise, the number 1.5. The exercise 1.6 is about the estimation of the spatial variation of the design storm ethograph. This is the most important of this exercise because that's going to be the input, the meteorological input to the hydrobit flood model. In this case, we're going to define the characteristics of the spatial variation of a storm associated with a 100-year return period for a given watershed that we're going to choose as an example. And then the estimation of the ISOjet that describes the spatial distribution of the centennial storm, that is the 100 years return period storm. Then the definition of the zones or polygons associated with the weights, which will be used in the hydrobit flood to define the spatial variation of the storm. And finally, we are going to compare those weights associated with the centennial storm and the weights associated with an historical storm that occurred in the year 1972 in that watershed that we choose as an example. Okay, I'm going to be swapping between QGIS and the presentation. The first of all, what we're going to do is we're going to open a new project, and then I'm going to QGIS project, a new project. And this new project, let's set project properties, selecting the CRS, that is a coordinate reference systems, and we are going to say that project as okay. Previously, what I did was I create this N1PA directory. We're going to say the project right here, and this is the data where there is the digital elevation model, but also we're going to have here the 100 years storm corresponded to that basin that we are using as an example. Okay, let's go to the project. We go to the properties. In the properties, we have to choose this Rekven UTM Zone 19 North, that is the 2202, that's the reference, the coordinate reference system that we are going to use. Apply. Okay, and now we're gonna save the project as, and then we're going to the we have to locate the directory. Here is the directory. Here is the directory where we are going to save the project, and the name of the project is going to be M1 P8, M1P8, similar as the name of the presentation. Okay, save. Perfect. Now we are going to add the digital elevation model. And to do that, we are going to add a layer. Let's go there, and then in the main menu we add a layer, and it's gonna be a raster type of layer. Okay. We browse, look for the directory. The directory is this one. Okay, inside the data, here is the DEM, open, add, close. Here we are the digital elevation model that we are going to use. And now, okay, what I'm going to do now is the DEM preparation. For that, okay, we have to check if the SRC is the RecBank UTM 19 North, and the pixel size. Okay, in the symbology tab, we are going to change the color of the DEM pseudo color monoband. We are going to use this color ramp BRBG, but we are going to invert the colors, classify and apply, and then the rest. Okay, let's do the. Let's going to do this. Okay. Okay, double click in this layer, and the double click. Okay, this is the information. This CRS is the chosen one. This pixel size, okay, 30 by 30 meters, basically. Okay. Now the symbology, we are going to change this to single band pseudo color. We are going now to choose this BRBJ, but we're going to change to invert the color ramp. Okay, classify, and that's it. Apply. Okay, just apply. Okay, this is the DEM. Now I'm going to change the transparency to 50% instead of 100%. 50%. Okay, we apply. Okay. Okay. Now we are going to create a hill shade version of this DEM. To do that, we're going to raster again. In raster on analysis, we select hill shade. Okay, the DEM is already selected. Now, all the default values, we keep the same values as default. Okay, now we are going to save that file. You have to be sure that we are in the right directory, and which is this one. And we are going to call this like dem underscore hill shade. Okay, dem underscore hill shade. Save. Okay, now we run the tool, close. Let's put this down. Okay, and then we're going to have a result like this. Okay, there's a combination between the colors, the different colors in the DEM, the original DEM, and the reason that we put a transparency of 50% is to reflect the effect of the hill shade DEM. Okay, now we got a result similar to like this one. Okay, now we are going to calculate the order of the string according to the methodology proposed by Strahler. To do that, we are going to the processing tab of the main menu. In the toolbox, we are going to look for this tool that is in Saga Terrain Analysis Channel, Strahler order. Okay, we select the DEM Strahler, and this is like here. Okay, now we are going to the processing Select toolbox. I already have the toolbox here. The zoom to a layer. Okay, we choose Saga. In the Saga terrain analysis channel, and okay, we select this tool, Straller Order. In Straller Order, the DEM is already selected, and the result. Okay, we are in the right directory, and we are going to call this dem underscore is trailer. Okay. Save and run. Okay, that's the the subroutine is running. Okay, perfect. Task complete. Close. Here is the result. We're going to have 9 orders. But to analyze, let's change the symbology using a single band pseudocolor, where the ramp that we're going to choose is blue. Okay, here there are the 9 orders of the Straller order. We apply. Okay, and we're going to get something like this. But as you see, there is too much detail here, okay? And then the way to reduce this detail, what we can do is go to the raster calculator. In the raster, we go to raster calculator, and we have 9 orders of water courses. These 9 orders, but we think that with 4 orders equal or greater than 4 is good enough to have a representation of the drainage network in the system. Okay, and then we're going to the raster calculator. Let's go to QGIS, raster calculator. We select then Straller over here, double click, and over here we are going to choose greater or equal to 4, the order. Okay, and the name of this okay, wrong directory. We have to choose the right directory. The name of this of the file is going to be river 4. Okay, let's go again to here to rivers underscore 4, because we are choosing orders equal or greater than 4. Save and okay, and okay. Okay, let's put this down here. River 4, double click. We're gonna change the symbology, single band pseudocolor. Okay, apply. Okay, okay. Okay, now we have the drainage network, but with a good detail that we can see the different rivers in the whole digital elevation model that we are using. Okay. Okay, the next step now is this is the result. The next step is to determination of this layer of drainage network and also basins, but in the vector format as a shape. To do this, we're going to use these Saga tools in terrain analysis channels that is called channel network and drainage basins. Okay. What we do is, to do this, let's go to QGIS. In terrain analysis channel, we are gonna choose now the channel network and drainage basin. Double click. Okay. The elevation. You have to choose the original dam. This is the original dam. Okay. Threshold is 4 because we want to that the drainage network be of order of 4 or greater than 4. Flow direction, not interested. Flow connectivity, no. Straddle order, we did this already. Drainage basin, but the drainage basin are in the raster format. We are not interested in the raster format. Channels, yes, we are interested in the channels in the shape format, and we're in the right directory, and we're going to call this rivers. Okay, save. And drainage basin, yes, in the vector format, and we're going to call these basins. Okay, shape. And junction, no, we are not interested in junction. And okay, perfect, that's it. We run the tool. Okay, it is running. And we're going to run the tool. Okay, task is complete. Let's go to, okay, it's complete, close. Okay, as you see, we have the different basins that are in this digital elevation model, and also the drainage network. In the case of the basins, let's change the colors. Let's choose transparent fill. Okay. And as a border of the basin, we choose this color. Let's increase this the size of the line at 0.35 instead of 0.26. Okay. On the other hand, the rivers, that is in yellow, double click, simple line. We're going to choose blue, a little bit darker, like this one. Okay. Apply. Okay. Now we have the different basins and the drainage network associated with each one of them. Okay, let's go to the presentation. Okay, we got this result. Now we're going to define a site of interest, that is this reservoir. There is a dam here. This reservoir is located exactly to this side. The dam site is has these coordinates, that x coordinate is this one and y coordinate is this one. Okay, we are going to use this information to delineate the watershed up to that site, up to the dam site. To do that, we are going again to the toolbox, Saga, Terrain Analysis, Hydrology, and we're going to select upslope area. Okay. As elevation, we are going to use the original DEM, the methods, deterministic 8, the output file we are going to call as area SD. SD because the name of the river that we are analyzing is Santo Domingo River, and this is going to be the Santo Domingo River Basin, and the reservoir is by the way, is a hydroelectric dam. Is a Santo Domingo Reservoir, and run the tool. Okay. Good. Let's go to, okay, now we're going to choose not terrain analysis channel or terrain analysis hydrology. And then the last tool is this one, slope area. Okay. The coordinate, the X coordinate is going to be 320,440.6 exactly. The Y coordinate is 982,412.3. Okay. The elevation we are going to use as elevation the wrong, this is the right, the original of them. Okay. The original of them. Okay. The method is going to be deterministic 8. Okay. Let's see if I need another information. Deterministic 8. Okay. Area SD is going to be the name of the output file. And then the output file, let's be sure that the directory is the right one. Yes. Okay, it's going to be area underscore SD Santo Domingo. Save. Okay, and then run the tool. Yes. Now it's working. Okay, that's complete. Close. Okay, here is the tributary basin to the dam site, to the Santo Domingo Reservoir. But this is in the raster format. Okay. To change this to the vector format in like a shape, we have to use the following. We have to apply the following procedure. We have to go to raster conversion and polygonize, and then we are going to obtain the delineation of the basin, but as a shape instead of raster in a vector format. Okay. And then choose the area SD, and the name is going to be SD basin shape. Okay. Let's go to raster conversion. It goes to raster conversion. Polygonize. Okay. Is area SD. Perfect. And the name is going to be SD Santo Domingo Basin. SD underscore basin. SD. Okay. Say to a file. The right directory is the underscore basin. Okay. Save. Run. Close. Let's close this and minimize this raster. And okay, the rivers is okay. The dam, the hill, shade. Okay, now we have this like a shape layer, but it's a vector. Vector layer. But if we um, uh, 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 if we see here the attribute of that layer, we are going to have two polygons, okay? The first, this polygon right here is the polygon that we are interested on. That is the basin of the Santo Domingo reservoir. And this one is the rest of the figure. And then we don't need this one. For this reason, we are edit that layer that is selected here, and we are going to select this polygon and erase. Okay, perfect. Now we save, and okay, we close the edition, and this is going to be the basin. Let's double click. Let's change transparent fill, and okay, let's choose this like okay, and apply. I'm going to have something now. Let's increase this. Okay, apply. Okay, yeah. Now we have this in as a shape, in a shape format. Okay, now the next step is with this eliminated. Perfect. Okay, the next step is going to extract the digital elevation model for the tributary basin to the dam site. Okay, to do this, we're going to use we are going to the raster tab, extraction, clip raster using the mask layer. Let me correct this. Extraction. Okay. Clip raster using the mask layer. The mask layer is going to be SD basin, the original DEM, and we are going to call the output file as DEM basin SD. DEM basin SD. Okay. Now we're going raster. Let's choose the DEM. Original DEM is this one. Okay. SD basin. We're going to raster, extraction, clip raster by mask layer. The input layer is going to be the original DEM, that is this one. This is in the directory of the project. Open. Okay, and the mask layer is going to be SD basin. Okay, that is perfect. Okay, and the name is going to be DEM basin SD. DEM basin SD. Then over here, save to a file that we are going to call DEM basin SD. Perfect. Save. Run. Okay. Okay. Close. Here we have the new DEM. Okay. Now let's change the colors. Double click symbology. Let's use the single band pseudo color. Single band pseudo color. We're gonna choose this as a color RAM BRBG. Okay. Okay. We're going to invert the color ramp. Okay. Apply. We have it here. Okay. 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 Now, the next step is going to, we have to clip this layer, rivers, to obtain the rivers only for for the Santo Domingo Basin. Okay. To do this, to do that, we're going to the vector tab, choose geoprocessing tools, and the tool clip. We are to select the rivers and the overlay layer is gonna be the basin, and the name of the output file is gonna be SD river. Now we go to the vector, geoprocessing tools, clip. Okay, the input layer is gonna be rivers. The overlay layer is the basin. The name is going to SD rivers. SD rivers. The name. Okay. Save to file. The right directory SD underscore rivers. Rivers. Okay, save, and we run the tool, close, and we have here the rivers. Okay, so we can change this, the color to a blue, a little bit darker, apply. Okay. Now we can close the rivers, close the river 4, and the dam. And we have as the basin. We're going to put it in the first place. Perfect. Now we have this the basin of the Santo Domingo reservoir. Now we can create also a hillshade of this Santo Domingo digital elevation model. That's raster analysis hillshade, layer raster analysis hillshade is the name of the basin. Okay, we are going to save to the file in the right directory, and we are going to call this the basin SD hillshade underscore hillshade. Save, run. We can move below the original dam, and the original dam we can change the transparency. The transparency is gonna be 50%. Okay, and here we are. We can the color is of this a little bit darker. Okay, apply. Okay. Okay, and this is the result. But we can increase also the size of the line that define the drainage network. And that's the result. Okay, with this we conclude or finish the first exercise, that is the delineation of the Santo Domingo River Basin. And now we will continue with the second exercise, that is the estimation of the spatial variation of the design storm. Well, the first thing that I'm going to do now is to upload this layer, that is the 100-year return period layer, that the name is SDT100. Okay, and then we're going to the to QGIS again. Now going to layer, add vector layer. Okay, we browse this, okay, go to the data. In the data we're gonna, okay, select this one. Is the T100 shape open? Okay, add and close. Okay, to do that, let's close this them. There's no need this them. Let's move it down here. Double click on that and SD100 layer. We're going to change the marker. Let's use this one. Their marker and then increase. Let's increase the size. Apply. Change the color. Let's use this color right here. Apply. And on the other hand, we need to look for this label, that is the precipitation in millimeters. Okay, we apply. Okay, then let's move a little bit this value, go to the placement, and instead of let's put 1 millimeter here, and that's it. Okay, let's go again, because double click, because the test we're gonna use ball. Okay, ball, that's better. Okay, okay. Well, what we have now is those are the rain gauges. The rain gauges, all of these rain gauges, let's close for a minute this. Okay, all these rain gauges, okay, all these rain gauges, they have the 100 years precipitation during for a duration of 24 hours, the 24-hour precipitation. With that information, what we're going to do now is, okay, we have this. What we're going to do now is to estimate the isojets that describe the spatial variation of the 100-year storm, the centennial storm. Okay. To do that, well, we are going to use this routine multi-level B-spline, and then we are going to Saga again. In raster creation tools, we select multi-level B-spline interpolation. Okay, with spline refinement. We have to check the output stem with SD basin. The cell size is 30 meters. And the output we are going to call T100 raster and run the tool. Okay. 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 Okay, let's go to QGIS. In QGIS, we are going to let's close this. Raster creation tools, and we select multi-level B-spline interpolation. The points is already selected this layer, that is SD100. The attribute is the precipitation in millimeters. The method is width refinement. What else? Okay, the cell size 30 meters. Feed nodes. We select nodes here. Let's check. The output stem. Let me define the output stem. We said to do this, we are going to use this layer that is SD basin, and that's the output stem. And the name of the output is going to be T100 raster. The name, say to a file, This is the directory of the project, T100 raster. Save and run. Close. Okay, now we're going to change the color of the rasters. We are going to consider this minimum value, maximum value, and 10 different categories to define the classification. Okay, let's go here. Double click over here. And now the symbology from six. No, let's change to the single band pseudo color. Let's choose the blue ramp. Perfect. And that is going from 60 millimeters to 240 millimeters. Equal interval. Let's increase the number of interval to 8. No, 10. 10. Okay. Apply. This is the raster. Let me check with what we have. Okay. Yeah, the same result. Now the next step is extraction. We're going to extract the isoidal map using a clip raster by mask of the layer, the raster layer that we call T100 raster. Okay, using as a mask SD basin. We go here. I'm going to raster extraction clip raster by mask layer. This is the raster I want to clip. The mask is gonna be SD basin. The output name is gonna be SD raster T100. Save to a file. SD raster T100. Save. Run. And close. Okay. Close this one. Let's change the symbology. Select single band pseudo color. We already have this blue color ramp between 60 and 200. 200. Equal interval. We're going to have 8 intervals. Okay. Apply. Okay, perfect. Okay. Now what I'm going to do is to extract the isojet. To do this, we are going to raster extraction contour lines, and we're going to select the SD raster T100, and every 20 millimeters. Okay, the attribute name is going to be precipitation raster extraction clip raster extraction contour. The right is the raster. The interval is going to be 20 millimeters. The name of the attribute name is going to be precipitation millimeters in parentheses, and we are going to call this SD isojet T100. Okay. Save to a file. Save to a file. Okay. SD ISOJETs T100. Save. Run. Close. Double click in ISOJET. Let's change the color of the ISOJET. Okay. Apply. Perfect. Let's increase this. So 0.35. Apply. Okay. Okay. I don't need this. We close this. But the ISOJETs are, we are going also to use some labels to identify the ISOJETs. Single label with the precipitation in millimeters. The test is going to be this. Let me put ball, and let's choose this color, like this one. Apply. That's the way that we can define the isojetal maps related with 100 years return period storm. Okay, let's continue. The next step now is the following. To compute the weights, we have to select the maximum precipitation. The maximum precipitation in this and the watershed is located here at the La Mitisus station. This Mitisus station, the 100 years return period, 24 hours precipitation is 192.8 millimeters. Yeah? Okay. To obtain the weights related with the polygons that are defined using the isojetal map, we are going to use this map algebra. And the way to do that is using the raster calculator. In the raster calculator, we are going to select the SD raster T100. Okay, double click, and all the values of this raster we're going to divide by 192.8. We have to be sure that we press this selected layer stem. The selected layer stem, and the output layer we are going to call SD weights T100 and press OK. Okay, let's go and then to the raster calculator. Raster calculator. In the raster calculator, we're going to choose the SD raster T100. Okay, we're going to choose SD raster 100. SD raster 100. That is right here, SD raster 100. And in the raster calculation expression, okay, we are going to divide this by 192.8. 192.8 is 192.8. Now we press this selected layer stem. And the output layer, we are going to call the output layer as SD weights T100. The directory is okay. SD weights T100, 100. Save. And okay. Okay, let's close this layer, the ISOJET. Let's double click on in this raster. We're going to change the color as a single band. So the color we're going to use now, the weights are going from 0.30 up to 1.0000. We are going to choose as a color ramp spectral. The spectral. Let me see if I A intervals. Okay, I'm going to use A intervals. SD weight 300. SD weight. Then we're gonna have equal interval. I'm going to choose 8 interval. Perfect. Apply. Okay, and we're gonna have something like this. Next step now is to define the contour related with the weight. And then we go to extraction, the raster extraction contour. We select the SD weight 100, define the interval in 0.10, and okay, raster extraction contour. The raster I'm going to use the contour lines at 0.10. Okay, the attribute name, weights. Weight, okay, and the name. The name is going to be output file. The name of the output file is SD weight 300. Say to the file SD weight 300. Press not diff because it's going to be okay, a shape file. Okay, save, run, close. Okay, double click. Okay, the color we're going to use black 0.35 in the case of the width of the line. Apply. But also the labels. The label, single label. We choose here the weight, the size, regular. Okay, for the ball. Apply. Exactly. In this way, what we did was first of all to define all the polygons that we can use in the Hydrobit flood application. Okay, and now with this weight we can compute the yetograph associated with which one of those polygons. Okay, now okay with this we finish the practice, but let's go to the presentation, and then in the presentation we reach this point, and this is a comparison between the weight of the centennial storm and the weight associated with an historical storm that occurs this April 9, 1972. And the idea is that for the Mitisus, the Mitisus station, rain gauge, we define the yetograph, the corresponding yetograph for the 100 years return period. And then we, for each polygon, what we do is we compute the mean weight. In this case, is 0.95. That multiply by the ordinates of this graph. We are going to have this result, and then we can compute these different graph for each one of the polygons. For example, in this case, the mean value of the weights is 0.45. 0.45 multiplied by the original ordinates of this graph is going to give you this as a result. And that's that's the way we can estimate the spatial variation of the precipitation in this case in the Santo Domingo Basin. Okay, here we have the temporal variation, and here we have the spatial variation. Okay, well, with this we finish the presentation. Thank you. Let's pass to the session of questions.